In this video, I'm going to explain how denormalized and special value floating point numbers are represented. I'll assume that you're already somewhat familiar with normalized floating point numbers and their representations. We have a separate video on that topic, but we'll review it very briefly here. For this video, we'll be assuming 32-bit floats, but everything we say can be applied with some minor modifications to 64-bit doubles. Recall that floating point numbers are effectively a variant of binary scientific notation, that is, numbers of the standard form shown here. There's a sign, plus or minus, and a real number constant c in a specific format, times some integral power of 2. For normalized numbers, c always has a single 1 to the left of the binary point. As we'll see, that's not true for denormalized numbers. In floating point format, numbers are stored in 3 fields: sign, exponent, and constant. The constant field is sometimes called the frac or mantissa. For 32-bit floats, we allocate 1 bit for the sign, 8 bits for the exponent, and the remaining 23 bits for the constant. Recall finally that for normalized numbers, the exponent is stored in biased form. That means that the range of possible exponents, minus 126 to positive 127, is shifted in the positive direction by adding a constant of 127. This ensures that the value recorded in the exponent field will always be positive. To recover the actual exponent, we just subtract the bias of 127. 2 of the possible 8-bit exponent values, namely 0 and 255, are not used for normalized numbers. For normalized values, you'll never see an exponent field of all zeros or all ones. Those 2 reserved exponent values are used for other types of numbers, denormalized numbers and special values, respectively. Let's first talk about denormalized floating point numbers, sometimes just referred to as denorms. First, notice that 0 is not a normalized value. Every normalized value in standard form has a single 1 to the left of the binary point, but there are no 1s in the binary representation of 0. 0 is an example of a denormalized number. The denormalized numbers form a special class of floating point numbers with very small absolute values, including 0. That means that they are very close to 0 on the number line. In fact, every denormalized number is smaller in absolute value than every normalized number. The smallest positive 32-bit normalized number is 1.0 times 2 to the minus 126. And the largest negative 32-bit normalized number is just the negation of that, namely minus 1.0 times 2 to the minus 126. Those are some pretty small numbers, so you can see that the denorms must be tiny indeed. All 32-bit denorms have the form plus or minus 0.b times 2 to the minus 126, where b is a bit string of length 23. The largest positive number of this form is 0.111, well, 23 ones after the binary point, times 2 to the minus 126. And the smallest negative value is just the negation of that. Notice that these are extremely close to the limits of the normalized numbers. In that sense, the floating point number system flows very smoothly from the normalized to the denormalized range. Every 32-bit denormalized number has an exponent of minus 126 and a constant of the form 0.b, where b is a 23-bit string. This is represented, as with normalized numbers, in our usual sign, exponent, constant format. But the value stored in the exponent field of a denormalized number is 0. Conversely, any float with an exponent value 0 represents a denormalized number. The sign is interpreted as usual, with 0 for positive numbers and 1 for negatives. Finally, the constant field stores the 23 bits following the binary point. there is an implied 0 to the left of the binary point. Let's look at an example. Suppose we have the hexadecimal string shown here and wish to interpret this as a 32-bit floating point number. In binary, this is the bit string shown here. Since the exponent field is all zeros, we see that this is a denormalized number. Since the sign bit is 1, it's negative. And finally, the constant is 0.11. Putting this all together, this represents the real number minus 0.11 times 2 to the minus 126. And putting this into standard scientific notation, this gives us minus 1.1 times 2 to the minus 127. Note that we couldn't represent this in normalized form, since the exponent is outside the normalized range of exponents for 32-bit floats. Finally, let's consider one last group of floating point representations, the so-called special values. Recall that there are two values of the exponent field that aren't used for normalized numbers, 0 and 255. We've already seen how 0 is used to represent denormalized numbers. 255, that is, all ones in the exponent field, is used to represent special values. If the exponent field is all ones and the constant field is all zeros, this represents a value of infinity, positive or negative, depending on the sign. These two values are shown here. If a floating point computation yields a value that's too large to be represented as a normalized value in either positive or negative direction, the machine may return a result of infinity with the appropriate sign. This is called saturation, and for many computations is often a better result than raising an error or returning a modular result, as in 2's complement arithmetic. If the exponent field is all ones, but the constant field is not all zeros, these are not legitimate floating point numbers. These are called nans, or not a number, in floating point jargon. If a computation returns a nan, something has probably gone wrong.